Okay, so we just finished talking about different types of covalent bonds, valence bond theory, molecular orbital theory, head-to-head overlap of orbitals generating sigma bonds, the sideways overlap of p orbitals generating pi bonds. Let's look at the influences of the different elements within these covalent bonds. So, and this brings us to polar covalent bonds. So electrons are attracted more strongly by one atom over another. And if the two atoms involved in the bond are exactly the same, like here just a generic X and X, or a carbon and a carbon, the electrons will basically be, it'll be a non-polar bond, and the electrons will be shared in between the two nuclei. It's basically a symmetric, completely symmetric bond. But what happens if one atom can pull those electrons to them, or has a greater affinity for those electrons than the other? And so what we've got depicted here with X and Y is that Y has got a stronger affinity for those electrons in this bond. And as a consequence, they spend more of their time closer to Y than they do closer to X. So this bond, all of a sudden, with the electrons closer to the Y, is no longer symmetrical, it's a polar bond. And what happens here is if the electrons are centered on one end versus the other, that means that like charges can start to be felt. So because this X is a little bit more naked than Y, X is going to start to develop a partial positive charge because, remember, X has got a bunch of protons in the nucleus. Here, with the electron cloud around Y, which bear a negative charge, this end of the molecule, or this end of the bond, is going to have a partial negative charge because of the negative electrons. So we call these polar covalent bonds. And here's a little example here. Carbon bonded to chlorine. Chlorine is more electronegative. So this bond is polarized towards chlorine. So I sort of spilled the beans here. This polarity is caused by differences in electronegativity. So the ability of an atom to attract electrons within a bond. So we've got some conventions here with this little delta plus, delta negative. These are what we call partial. So partial positive, partial negative. Partial positive charge, partial negative charge. The extreme example of this is just basically electron transfer. So Z is far more electronegative than X. X just gives up the electron and you form a covalent bond. So a situation like lithium chloride. So it's in between. So a polar covalent bond is in between the extremes. Okay. So electronegativity, the ability of an atom to attract the shared electrons in a covalent bond. This is very similar than electron affinity, which was an experiment done in Gen Chem, which dealt with an atom attracting electrons in the gas phase. And it mirrored electronegativity quite closely, but in this case, it's the ability to shift electrons towards them in a covalent bond. So you can think of it as a tug of war where two sides are pulling on the string and one side is losing, right? So that is, so it's going to be differences in electronegativity which generate these polar covalent bonds. You can have, so do we remember which element is the most electronegative? And the answer is fluorine, right? So as you go from left to right across the periodic table, the electronegativity increases. As you go from the bottom to the top, the electronegativity increases. So fluorine is the most electronegative atom, and the atoms on the far left-hand side are what we call the most electropositive atoms. So they're the ones willing to lose their electrons quickest. So it was Linus Pauling which basically developed this scale of electronegativity. The textbooks have got, the numbers are very close. Some might vary by a decimal, like 3.5 versus 3.4. We don't need to memorize the numbers or anything like this. All we need to know is which ones are the most electronegative. So fluorine, then oxygen, and we got chlorine and nitrogen. So going across the first row, boron is the least, carbon, nitrogen, fluorine, so to speak. Hydrogen's up over here, but it sort of fits in between boron and carbon at around 2.1. And as you go down the periodic table, this number tends to decrease. What we're going to see later on in the course is that even atoms like iodine, which are below boron, they've got another characteristic which makes it seem like they're electronegative. So that's something to keep in mind in the future. But, so carbon versus fluorine, that type of bond is going to be polarized, and fluorine is going to be pulling the most electrons towards it. So carbon will have the partial positive charge. Yeah, so basically, yeah, that is what we wanted to talk about. So 4 was the maximum, and less than 1 would be a really electropositive atom. Okay, now, in the case of, so if we took sodium and chloride, like we did previously, that is salt, right? An ionic bond. So if the difference in the two numbers is large, then you form an ionic bond. If the difference in the numbers is less than 0.5, these bonds are considered to be symmetrical or nonpolar. So a carbon-carbon bond, they've got the same electronegativity, so that would be a nonpolar bond. But hydrogen and carbon, you'll see that the electronegativity value is very similar. It is a non-polar bond. So carbon-hydrogen bonds are non-polar. Carbon-carbon bonds are non-polar. But if you've got carbon and nitrogen or carbon and oxygen where this is getting bigger than 1.5 or equal, then you start to have polar covalent bonds. So carbon-hydrogen, non-polar bond, carbon-carbon, non-polar bond, chlorine-chlorine, because the difference between 3 and 3 is 0, non-polar bond. But if it's in between this magic range of 0.5 and 1.7, we call these polar covalent bonds. Now, there's basically a little convention we use, and anything over 1.7 is an ionic bond. There's this little convention that we use with this little arrow with a plus little hilt on it. And you point this in the direction of the more electronegative atom. So it's it's easy to remember which end has got the positive charge because we've got a little plus right here. So that'll be the partial positive side, and the pointy end will be the partial negative side. So when carbon is bonded to fluorine, remember fluorine is the most electronegative, this bond is going to be polarized in this direction. Fluorine will be the delta minus, carbon will be the delta plus. So carbon, when we say delta plus, it's basically this carbon's electron poor, right? Because all the electrons are shifted over towards the fluorine. Conversely, if we go back and look at lithium, which has got a electronegativity value of 1, comparing that to carbon, which carbon's got 2.5. In this case, if carbon's bonded to lithium, it's the lithium which is got the partial positive charge, and it's carbon which has got the partial negative charge. So this bond is polarized in completely the opposite direction. So in this case, carbon's the electron-rich atom, and lithium would be the electron-poor side of the bond. So the chemistry of methyl lithium versus fluoromethane over here is completely different, because in one instance with the methyl lithium here, carbon's got the partial negative charge, is electron rich. And in the other instance, carbon's got the partial positive charge, which is electron poor. So remember, in our class, our mantra for the class is negative goes to positive. So if the species here, methyl lithium, was involved in a reaction, well, we know where the electrons are. They're on this carbon. They're going to be reacting with whatever. So it's going to be doing the attacking. Whereas over here, where this has got a partial positive charge, this carbon, in this instance, is going to be the attacked, because it's something with electrons is going to attack that because it's got the partial positive charge. So what we're going to be able to do going forward is we are going to be able to, it's just like a giant jigsaw puzzle. We're going to be connecting negatives to positives. And it's gonna basically describe the chemistry of the various different atoms that we have. So the next part deals with if you've got anything above 1.7, I said this before, you've got an ionic bond. Nice example here is sodium hydroxide. The difference in electronegativity between oxygen and sodium is greater than 1.7. So oxygen's bearing a negative charge. Sodium is bearing a positive charge. That would be a pretty straight up example of that. Now, whenever you've got electrons shifting, the electron density shifting towards one atom over the other because of electronegativity, this is what we call an inductive effect. So later on, when we're talking about acids and bases, we're going to be able to look at a structure of a molecule and determine how acidic it is or how basic it might be. And inductive effects become an important sort of important factor in this. So inductive effects take place through sigma bonds. So if electron density in a sigma bond is shifted towards one atom because of an electronegativity difference, we call this an inductive effect. So if electrons are being pulled towards that atom, we say that that's an electron withdrawing effect. And if electrons are being shifted towards another atom, we call that electron donating effect. So electron donating or electron withdrawing effects are basically transmitted through sigma bonds, and they are depending upon the inductive effects based upon differences in electronegativity. So the most electron withdrawing group, fluorine, has got an electron withdrawing inductive effect, whereas lithium, for example, would have an electron donating effect because it's electropositive and it's pushing away its electrons. So electronegative atoms withdraw electron density, electropositive atoms donate or release electron density. Yeah, that's because the Linus-Pauling scale is about electronegativity. It's the more common used term is a withdrawing effect. The electropositive atoms, we just say that that's a donating influence. Okay, now you can have polar bonds, but you can also have polar molecules. This little section here, like we've got some, I got water molecule, ammonia, carbon tetrachloride. All of these molecules possess polar bonds. Some of them are polar molecules, some of them are not. The net polarity in a molecule is called the dipole moment, and there's a measure for it. Water is one of the most, it's got one of the strongest dipoles there is. So it's got this, its unit is very high. It is really important in the lab, and this, you'll do a lab later on, which deals with solubilities based upon polarities of the solvent and of the molecule. So the other thing you need to do, figure out how to do this type of thing, is remember the three-dimensional structure of a molecule, which is Vesper theory, which we'll talk about next. Or yeah, we'll talk about that next. So carbon tetrachloride is tetrahedral. All of these bonds, they cancel each other out. The polarity of all these bonds cancel each other out. So it's a non-polar molecule, whereas with water, this bond's polarized, this bond's polarized, the lone pairs are electronegative. So this molecule's got a net dipole in a specific direction. But this is like getting the three-dimensional structure plus the bond polarities. That's really important in the lab. And we'll talk about that. So for what we're talking about for this lecture is really about recognizing, if I'm looking at this bond, is it polar or not? Am I looking at this bond, is it polar or not? That's the first trick. Then we're going to add on the layer of what's the actual geometry of the molecule, and that's going to provide us with some insight as to if the molecule will be soluble and that sort of stuff in the lab. All right. Okay. Next thing I guess we got to talk about is drawing Lewis structures and Vesper theory, valence shell electron repulsion. All right.